We assume buying highly engineered steel is a guarantee. You take the tool out, close the jaws, and trust the number it gives. But the truth is, almost every standard 6-inch caliper resolves to the exact same tolerance, 1/1000th of an inch, or 0.02 millimeters, whether it costs $20 or $200. The market asks you to trust one of three mechanical architectures: vernier, dial, or digital. The defining difference between these architectures lies in how their internal mechanics react to the dust, fluid, and impact of the shop floor. Choosing a caliper based purely on the price tag, or how easy the screen is to read, ignores the physical reality of the tool. If you put the wrong mechanics in the wrong environment, you destroy your precision before you ever take a measurement. Calipers violate the Abbey principle. The measuring scale is on the beam, but objects are measured at the jaw tips. This distance creates a lever arm. Normal wear lets the sliding carriage tilt slightly. That tilt multiplies down the jaws, creating massive, invisible measurement errors. Because calipers are compromised by this structural reality, your only defense is to manage the wear on the tool. That means matching the internal mechanics of the tool to the specific hazards of your workspace. For the harshest industrial environments, the standard is the Verniercalliper. It has 0 internal moving parts. Instead, it relies entirely on human visual hyperacuity to line up a sliding auxiliary scale against a fixed main scale. Because it is essentially a solid piece of machined steel, it is immune to magnetic fields, to heavy coolants, to physical shocks, and dead batteries. That durability comes with a specific trade-off: parallax error. To prevent the sliding plate from grinding against the main beam, there is a tiny physical gap between them, known as the step height. If you view the scale from a slight angle instead of looking perfectly straight down, that step height causes the alignment marks to visually shift, resulting in a false reading. The vernier gives up reading speed and ease of use to guarantee absolute mechanical reliability in dirty, heavy machining conditions. In environments where speed is critical, you find the dial caliper. This tool translates linear sliding movement into rotary movement using a highly precise rack and pinion gear train hidden inside the carriage. This gives you instant visual feedback. You can also rotate the dial bezel to set a 0 point against a master part, allowing you to easily read the plus or minus deviation on subsequent parts. However, the main beam has an exposed gear rack running right down its center, which acts as a trap for debris. If a microscopic chip of metal, or swarf, gets wedged in those teeth, the internal pinion gear will ride over the obstruction and physically skip a tooth. A single jumped tooth permanently shifts the tool's 0 point by exactly 0.025 inches. Every measurement you take after that will be corrupted. The dial caliper offers excellent speed and utility, but you can only trust it if your workspace is free of abrasive dust and metal chips. For modern quality assurance, the highest throughput option is the digital caliper. Physical gears are replaced by a capacitive stator-rotor encoder that instantly translates sliding movement into clear digital numbers. This completely eliminates the operator parallax error of the vernier scale. It allows for instant millimeter-to-inch conversions, and the data can be ported straight into statistical tracking software. But the electronics introduce their own fragilities. You are entirely dependent on a finite battery supply, and exposure to heavy magnetic fields or liquid coolants often shorts out the internal encoder. The digital caliper trades the standalone durability of analog steel for high-speed logging and digital integration. Whether you rely on an LCD screen, a dial, or a physical scale, the underlying steel chassis guiding the tool degrades in exactly the same way. Inside every caliper is a friction pad called a gib. This pad is controlled by small set screws and regulates the clearance between the sliding carriage and the beam. Thousands of sliding passes slowly grind down that gib pad. This creates a gap, reintroducing mechanical play that radically multiplies the Abbey error out at the measuring jaws. To eliminate this wobble without causing the slide to bind, operators have to routinely test and tighten the set screws. A caliper is a kinetic mechanism. If you do not actively maintain its physical clearances, the tool will lie to you. This chart plots measurement throughput on the horizontal axis against environmental resilience on the vertical axis, giving us a matrix to match the tool to the reality of your work. If you are a quality assurance inspector logging hundreds of pristine parts into a database, the digital caliper's speed and direct data output make it the optimal choice. If you are an industrial machinist working near heavy coolants and flying swarf that would shred an exposed gear rack, you need the absolute resilience of the Verniercalliper. And if you are a custom fabricator or a woodworker taking rapid differential measurements in a dry, chip-free shop, the dial caliper gives you battery-free speed. The right tool is simply the one whose mechanical weaknesses are best protected by your specific environment. Buying the correct architecture is only the first step. Verifying that the tool is actually measuring true is the ongoing requirement. You start with a daily check, holding the closed jaws up to a light source. If any light leaks through, the jaws are warped and no longer parallel. Beyond that, calipers require annual ISO 17025 certified calibrations against traceable gauge blocks to legally prove the tool hasn't drifted past its maximum permissible error. Absolute precision doesn't exist out of the box. It's earned through aligning the mechanics, controlling your environment, and verifying your data.